We're going to introduce the idea of voltaic cells. Voltaic cells are also known as galvanic cells, and they're also known as batteries. So to discuss voltaic cells or galvanic cells, we're going to use the same reaction we've been looking at as our example all along. We have solid zinc reacting with copper 2 ion to form copper solid and zinc ion. So in this particular example, we have zinc being oxidized. It is giving its electrons to copper 2 ion so that zinc forms zinc 2 ion, and copper is being reduced to copper solid or elemental copper or copper metal. So this is a reaction that you did in the lab, and in the lab you did it all in one container. You had copper 2 ion mixed with solid zinc, and you observed a reaction where solid copper formed and zinc ion replaced the copper ion. So the solution got lighter blue, and then you saw signs of copper solid being formed. Now, if instead of performing this in one reaction, we can create a voltaic cell by separating the two half reactions into their own compartments, which we call half cells. So we're going to separate this where the zinc oxidation half reaction will occur in its own compartment, and that would look like this, where we have zinc metal combined with zinc ion. And then the reduction half reaction we're going to put in its own compartment where we have copper metal combined with copper 2 ion. If we connect these two, so in the bottom you see the half reactions that occur in each compartment. We connect these two with what's called a salt bridge. This allows the ions to flow across between the two half cells so that the electrical charge inside each cell is 0, because that is a requirement. We can't build up charge on either side or else the reaction will not take place. Now if we connect these two pieces of metal, which we'll call electrodes, with a wire, then the electrons that are formed on the left-hand side in the oxidation half cell, which we call the anode, when those form, because this reaction takes place, that electron will travel across to the cathode, where it will be used to reduce copper 2 to copper solid. And so the two separate reactions occur. They are connected with each other by the salt bridge, which allows ions to pass, and they're connected by a wire, which allows electrons to pass. Now, these electrons flowing, we can use these electrons, which spontaneously flow, to do useful work. We can use the energy that's produced to do electrical work, right? We can light that light bulb, or we can power your cell phone, or we can power your car, or whatever. Okay, so these are the batteries that you buy at the store. Okay, a battery that you buy at the store has separate compartments inside it that allow different spontaneous reactions to occur, and they allow electrons to be produced at one of the electrodes, which was just one side of the battery. It's either one of the little circles on the top of the 9-volt battery, or it's one end of, say, a AA battery, right? One end is positive, one end is negative. The anode is just by definition the electrode compartment, the half cell where the oxidation half reaction occurs, in this case zinc, forming zinc 2 ion. And then the cathode is by definition where the reduction half reaction occurs, which in this case is copper 2 being reduced to copper solid. I remember that the anode is where oxidation occurs because anode and oxidation both begin with vowels. Cathode and reduction both begin with consonants, and that's just the way I remember it. Or if we take the salt bridge away, what happens is we build up charges inside these compartments, and that is it's not allowed, right? So we can't have positive ions being formed on the left that aren't balanced by negative ions flowing inside. And so if you take that salt bridge away, then of course the light bulb will no longer light, because the reaction will cease to. So we're going to diagram another voltaic cell just as practice. Here we have copper reacting with silver. We saw this was our first reaction that we looked at when we looked at evidence of a redox reaction. This was the demonstration we did. We need to transfer 2 electrons from copper solid to form copper plus 2, which means we need 2 silver ions, which is why we put the 2's in there. We separate this into 2 half reactions, copper forming copper 2 and 2 silvers forming 2 silver atoms. And then we're going to label the anode and the cathode. Oxidation occurs at the anode. Reduction occurs at the cathode. And if we draw our half cell with the beaker and we put our copper metal in there and our copper 2 solution, remember that copper 2 is blue. And so over time what's going to happen as this cell discharges once we connect it to the cathode is copper solid is going to form copper 2, which means that over time our copper electrode will actually get smaller and smaller and smaller in mass, and the copper 2 ion, since it will increase in concentration, this side will get more and more blue. Reduction occurs at the anode. If we draw this reaction, we have silver ion in a beaker, silver solid in a beaker with silver cation around it in the solution. So in this case, the silver ion will be reduced to form silver solid. So over time, the silver electrode will get larger and the silver concentration will go down in the solution. So I'm going to label the anode. I'm going to put the half reactions underneath each half cell. If we connect the electrodes with a wire, we know that electrons are formed on the left-hand side, so they're going to travel from the anode to the cathode. So the direction of electron flow is from left to right in this case, because they're formed on the left and consumed on the right. We have a salt bridge that we need to add. I'm going to put that in gray. And I know that because cations are formed on the left-hand side, they're going to need to flow out of that side. And so cations will move from left to right toward the cathode, and cations are consumed on the right-hand side. So they're lost. That's what that says, is cations are lost in the cathode compartment, which means that cations have to flow from left to right, anions must flow from right to left. And that is to balance out the charges that form. This is an example of a voltaic cell. This is the example that we use to introduce voltaic cells, where we have copper 2 being reduced on the left in the cathode compartment and zinc being oxidized to zinc 2 in the right, on the right in the anode compartment. This is just reversed from the one I showed you, where in my cartoon the anode was on the left. So here the only additional feature that I didn't show in mine is the salt bridge. Now, if you look at the left-hand side, the copper 2 is forming copper ion, which means what happens there is that we're losing cations. So cations must flow into the left compartment, and anions must flow out of that compartment. So you should be aware of the flow of the ions. Now, cations always flow into to the cathode, and that's the reason they're called cations, is because they flow to the cathode. Anions always flow to the anode, but it's kind of important that you understand that it's because we're losing copper 2 ion that we have to move more cations into that compartment or move anions out of that compartment. On the right-hand side, we have zinc ion forming, which means that we would build up positive charge if we didn't have negative ions flowing into that compartment or positive ions flowing out. This shows you that if we connect this these two electrodes together and we measure the potential using a voltmeter like you see here, then we would see a voltage of 1.10 volts. And we're going to discuss how you would calculate these values based on standard reduction potentials that we'll talk about soon. This is just another example of a voltaic cell. The left-hand compartment has iron forming iron 2. That is the anode, because that's where oxidation occurs. And then the right-hand compartment, you have iron 3 being reduced to iron 2. So this is just an example of sometimes you have cells where you don't form a solid, right? The right-hand compartment, the cathode is still a reduction, but it's not forming iron solid, it's forming iron 2 ion. And so in a situation where you do not have a solid metal, then what you use instead is we use platinum as the metal that would accept the electrons and then release them to the iron 3 to form iron 2 to allow for the reduction to take place. And so sometimes we do use platinum when there is not a solid metal involved in the in either half reaction. And so you see platinum as a cathode or an anode for aqueous reactants forming aqueous products, or when you have a gas that is either reacting as a reactant or forming as a product, like hydrogen gas. We'll see that for the standard hydrogen electrode. This is just another example of the anode on the left. Chromium is being oxidized to chromium-3. It is releasing 3 electrons. Those electrons are traveling through the wire, and they will be used to reduce 10(2), SN2+, to form 10 solid. This is just another example of a galvanic cell. Next, we're going to introduce the idea of the standard hydrogen electrode. We use the standard hydrogen electrode in order to measure reduction potentials of all the different reduction half reactions that occur. Now, sometimes the standard hydrogen electrode will be the cathode, and sometimes it'll be the anode. Hopefully, that'll make sense by the end of this discussion. The standard hydrogen electrode is abbreviated SHE, or SHE. It seems kind of, I don't know, seems like the girls are getting the better end of the bargain there. Sorry about that. This reaction shows the oxidation of hydrogen. So this would occur at the standard hydrogen anode. When the SHE is an anode, it would look like this. So we have hydrogen gas being oxidized to hydrogen ion. So this is the oxidation of H2. In this case, we need a platinum electrode, which is an inert metal that will be used to transfer the electrons. Here we have hydrogen gas that's bubbled in from an outside source. That hydrogen gas is present under standard conditions at 1 atmosphere. And then hydrogen ion would form, and it would increase the hydrogen ion concentration in the solution. It would lower the pH. So those would form. So hydrogen gas is the reactant, and H plus is the product in this case for the oxidation half reaction. Or the reaction might occur in the opposite direction depending on what the electrode is paired with. So the reduction of H plus would be the opposite reaction. So in that case, we're going to erase this, and we're going to say H plus goes to H2. And this, instead of being the oxidation of H2, this is the reduction of H plus. This would occur at the cathode. The one that occurs is going to depend on what we're paired to, okay, what we pair it to. So if the reduction occurs, then the SHE is the cathode, is what that should say. If oxidation occurs, then the SHE is called the anode. So down here this should say cathode, but it doesn't. So reduction always occurs at the cathode. The reaction that occurs will depend on the other half cell that's paired to the standard hydrogen electrode. And we can use the reduction potential table to look at that. So the reduction half reactions at the top are more likely to occur as reductions as a cathode when paired to the SHE. The SHE will be the anode in that case, and it's marked by this green asterisk. These reduction half reactions at the bottom would actually occur in the opposite direction as oxidations instead. These half reactions would occur in the opposite direction. The SHE would then be the cathode in that case. So it all depends on the more likely reaction. To the previous slide, copper metal will not be oxidized by hydrogen because it is less active than H2. However, zinc is more active than H2, which means that it's more likely to react the way is shown here, right? So zinc will be oxidized as the anode. So whatever you pair the standard hydrogen electrode to the SHE will either be the cathode or the anode, whatever way it needs to be in order to have a spontaneous reaction occur. Now we use the standard hydrogen electrode in order to measure and record in a nice little table like this one the standard reduction potentials. Now you see at the top has the highest reduction potential, fluorine, and the very bottom is lithium, which has the most negative reduction potential. So what you need to know is that the reduction potential, which is abbreviated capital E, the little degree sign means standard conditions, which for thermodynamic standard conditions, that's 25 degrees Celsius, 1 molar concentrations, 1 atmosphere pressure. The positive numbers represent spontaneous reduction half reactions, and then the negative numbers would be less likely to occur. They'd be more likely to produce a non-spontaneous overall potential. You can see hydrogen in the very middle. We set that as just a standard to be as 0, and therefore anything that's that's a positive value is more likely to be reduced than hydrogen. So if the half reactions above that green bar that represents hydrogen right in the middle, anything with those positive reduction potentials, if you paired them with hydrogen, they would be reduced at the cathode, and hydrogen would serve as the anode. So the example we had earlier was copper, right? Copper is 2 positions above hydrogen. So if we paired a copper electrode with the standard hydrogen electrode, we know that the copper would represent the cathode because that's the reduction half reaction that we see here. However, when we paired zinc with it, zinc is about 1, 2, 3, 4, 5 reactions below hydrogen. It has a negative reduction potential, which means that it would actually be oxidized in the presence of the standard hydrogen electrode. Because its reduction potential is negative, its oxidation potential would be positive 0.76. That would be the opposite reaction, solid zinc forming zinc 2 plus 2 electrons. There's a shorthand notation that goes with voltaic cells that I wanted to talk about briefly. So this is our reaction that we looked at earlier where silver is reduced and copper is oxidized. This oxidation is going to occur at the anode. 2 electrons are involved in this oxidation. Silver will be reduced at the cathode. 1 electron per silver ion will be transferred, which is why we need 2 silver ions. Remember, the number of electrons transferred has to be the same. They don't just poof, vaporize. Shorthand notation for this cell, the anode is always listed on the left-hand side. And everything kind of goes in the order that it occurs. And so the solid copper is on the left, and that's true in the reaction as well. Vertical lines represent phase boundaries, meaning between the solid and the aqueous. Different phases would have a vertical line separating them. And then there's a double line that represents the salt bridge. So that's basically the separator between the 2 compartments. And then the cathode is on the right-hand side. And again, it's in the order that the reaction occurs. And so silver ions on the left, there's a vertical line that separates the phase boundary, or that represents the phase boundary, and then silver solid is on the right, just like it is in the reaction. Silver ions on the left, silver solids on the right. So that's the way I always remember, is that it's always sort of left to right in the shorthand notation the same way it is in the reaction. So the general setup, you have electrode material, aqueous stuff, and electrode material. So the electrode material is always on the outside. Anode's always on the left, cathode's always on the right. So the electrode material has to be something conductive, right? So typically there is a solid metal involved in the reaction. That's not always true, so this might be platinum if there is not a solid metal involved in the reaction. Aqueous ions are assumed to be 1 molar. If they are not, then that would be included in the shorthand notation. So it would have a parentheses that would say 0.5 molar. Now, this something conductive is often part of the half reaction, but it is not always part of the half reaction. So, for example, here we have 10,4 being reduced to 10,2. That is the cathode or reduction half reaction. We have magnesium solid being oxidized to magnesium plus 2. So the oxidation is the magnesium. The reduction half reaction would be 10,4 going to 10,2. So we're going to, and of course there's 2 electrons involved in the transfer. 10,4 must gain 2 electrons, and it takes them from magnesium. So we're going to write the anode first on the left. Magnesium solid is the anode material, the metal. Magnesium ion, there's a vertical line that separates the 2 phases. 1 molar is the concentration. That's sort of redundant. Often it's not included. If it's not standard, it is included. That vertical double line is the salt bridge. And then we have 10,4 going to 10,2, and you list them in the order. So 10,4 is on the left and 10,2 is on the right, the same way it is in the reaction. And then there's another vertical line to separate this cathode material, to separate this aqueous compartment from the cathode material. But in this case, there's no solid 10 being formed, which means that we need to use some sort of non-reactive conductor. And you kind of just have to know that it's going to be platinum. That's sort of the standard non-reactive conductor that we use. Sometimes we use solid carbon, graphite. Okay, practice. Voltaic cell practice, to be more specific. Here we have a reaction, and we're going to consider it in the direction that it is written. I'm going to start by balancing it. Chromium has 3 electrons that it needs to gain to form chromium solid, whereas copper will only lose 2 electrons to form cobalt. Cobalt will lose 2 electrons to form cobalt-2 ion, which means we need to balance the number of electrons involved. Instead of 3 electrons or 2 electrons, it needs to be the same number, so we need to make that a 6. Which means we need to have 2 chromiums and 3 cobalts. Here we've drawn arrows where the blue is the reduction, which is going to occur at the cathode. The red is the oxidation, which will occur at the anode. Here I'm trying to show you that the number of electrons involved in each half reaction is not the same. So we're going to use coefficients to make them the same. These coefficients make it 6 electrons being transferred. This is the balanced reaction. Now when we draw the schematic, we have an electrode compartment on the left and on the right. We can worry about labeling it once we get everything situated in here. So the anode on the left is our oxidation half reaction. So we're going to have solid cobalt forming cobalt ion. Solid cobalt is the metal we've drawn here. Cobalt ion will be in the solution. And the arrow will go in this direction. 6 electrons will form each time 3 cobalts are oxidized. Our cathode compartment is going to involve this half reaction, chromium-3 going to chromium solid. We need 2 of them. So chromium-3 in the solution to chromium solid on the metal, which is the the cathode material itself, the metal. So 2 chromium ions plus 6 electrons form 2 chromium solid. Now if we connect these 2 with a wire, electrons will be created from the anode, in the anode compartment. You can see that because they are products. Electrons are formed in the left compartment, and they travel to the right-hand side where they are used to reduce 2 chromium ions. So they are consumed in the right-hand compartment the way we've drawn it. You could have drawn it the other way, but then you would draw the electron flow going the other way. This is my salt bridge in gray. Since chromium is formed in the cobalt forms on the left-hand side, that's a cation. And cations are consumed in the right-hand compartment, which means we need to have cations flow from the left to the right. That way it replenishes what you lost on the right-hand side, and it counterbalances what you gained on the left-hand side. Or you'd have anions flow from right to left. Now we're going to calculate the potential of this cell. We're going to start with the reduction half reaction for chromium. We're going to look up its reduction potential in the table. Find the element, chromium. This is its reduction half reaction for the one that we've drawn, negative 0.744. Now we have the oxidation half reaction that we need to write, cobalt going to cobalt 2 plus 2 electrons. If we go back to our reduction potential table and we find cobalt, it's down here at the very bottom. Now, of course, it's written as a reduction half reaction, as all the reactions are on this table. So if we write down the reduction half reaction and the corresponding reduction potential, this is related to the oxidation half reaction because it is the opposite, right? So this one we wrote at the bottom is from the table. We reverse it to get the oxidation half reaction, and we change the sign to get the oxidation potential. So these top two reactions are what we add together to get the overall reaction, which means we add the two, we sum these two, the reduction potential and the oxidation potential, and that gives us the overall potential, which is negative 0.464 volts. This is a non-spontaneous process the way we've written it. So the answer is no, it is not spontaneous because, we're rounding to negative 0.46 volts because of the 0.28. So now we're answering the question, is the reaction spontaneous? And the answer is no, because it has a negative potential. E is negative. Part D, calculate delta G. So from part C, we know the potential of this cell is negative 0.464 volts. We use this equation, which is on the yellow sheet. And you're going to plug in number of electrons transferred for N. That's moles of electrons transferred. In this case is 6. F is Faraday's constant, which is in the fourth one down on your yellow sheet. And then we plug in all the numbers that we need to plug in. And we get 268,614 joules per mole. We're supposed to convert that into kilojoules per mole, which means we need to divide by 1,000 to turn that into, it appears to be 269. Oh, it's going to be 270, I think, because it only has 2 sig figs, right? The 6 is exact. Faraday's constant is more accurate. This really only has 2 sig figs, so I believe it's going to be 270 kilojoules per mole, or 2.7 times 10 to the second. This is a non-spontaneous reaction. We've already decided that. And the answer is no. I wouldn't buy this battery because it would not work.